I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll briefly discuss about the understanding of the foundations of probability theory. The probability theory is the mathematical framework that deals with analyzing random phenomena and quantifying uncertainty. It provides tools to calculate the likelihood of various outcomes, enabling better decision making in uncertain situations. The core concepts include sample spaces, events, and probability measures, which help in modeling and predicting real world scenarios. Understanding these foundations is essential for applying probability effectively in fields like artificial intelligence, machine learning, and data analysis. We'll see one by one. First, we'll move on to the introduction about the probability. What is probability? Probability is a branch of mathematics that focuses on quantifying the likelihood of different outcomes occurring in uncertain situations. It provides a systematic framework for analyzing and predicting the chances of specific events based on available information. Probability, see, all you know that the probability is expressed. How we are going to express the probability? So we are expressing the probability in terms of zeros and ones. Let me explain. The probability is expressed as a value between 0 and 1, where 0 indicates a impossible event. Impossible event, and 1 represents a certain event, that is the predicted certain. This we should know very clearly. Certain event. For example, in a coin toss, the probability of landing heads is so if you are tossing a coin, the probability of a head, we are representing it as a P of H, is equal to 0.5. There are two options only, meaning that there is a 50 percentage of the chance of this outcome. By using probability model, we can what we can do, we can access and predict outcomes in situations where complete certainty is not possible. Next, why is probability important? The probability is essential for various fields like including artificial intelligence, AI, machine learning, ML, and data science, statistics, finance, and many others, where decisions need to be made under conditions of uncertainty. In AI and ML, probability helps models make predictions, classify data, and handle incomplete or noisy information effectively. In finance, it assesses risks and models market behavior, while in data science, it aids in drawing meaningful insights from data. By providing a mathematical framework for uncertainty, probability enables us to make informed rational decisions and improve the accuracy of predictions in complex systems. Next, what is the importance of probability in autonomous vehicle? In the previous slide, we were been discussing about uncertainty under that is the uncertainty occurs in the autonomous vehicle system. Why it is important? The probability is important in autonomous vehicles. See, only know that the perception and object detection, what will happen? Autonomous vehicle, if you are taking, it rely on perception system to detect and identify objects in their surroundings, such as other vehicle, pedestrians, and obstacles. These systems use sensors data from cameras, lidar, and radar, which are inherently noisy and uncertain due to environmental conditions, sensor limitations, and that is occlusions. Probability models helps the vehicle estimate the likelihood that it will detected object is correctly identified and assess its position, size, and movement. For instance, probabilistic techniques like Gaussian mixture models that we'll be discussing in detail in the later slides. Gaussian mixture models, we are shortly representing it as GMMS, Gaussian mixture models, hidden Markov models, that is HMMS, are used to model uncertainties and enhance perception accuracy, ensuring safe and reliable operations. If you are considering the sensor fusion, no, sensor fusion is a critical aspects of autonomous driving that combines data from multiple sensors. What are all the sensors? We'll be using lidar, radar, and cameras to create a unified and more accurate representations of the environment. Each sensor has different strengths and weaknesses, and their output may conflict or to be incomplete. Probability theory, particularly through Bayesian filtering, this we'll discuss in later, techniques like Kalman filters and particle filters allow the system to update and refine its beliefs dynamically based on new observations. By assigning probabilities to different hypotheses and fusing data, the vehicle can make better informed decisions, reducing the uncertainty associated with the raw sensor data. Next, decision making and risk assessment. So, if you are taking path planning and navigation in the autonomous vehicle, path planning and navigation, no, it involves predicting the potential future trajectory features of trajectories and the way of autonomous vehicle and other surrounding agents such as vehicles, cyclists, and pedestrians. Given the uncertainty in the environment, the vehicle must evaluate the probabilities of different outcomes and select the safest and more efficient route probability models such as Markov decision process MDS and partially observable MDPs. Partially observable MDPs, that we are calling it as POMDPS, helps the vehicle assess collision probabilities and balance the safety with the performance. These models allow the vehicle to dynamically adjust the trajectory by considering both immediate risks and long term safety. Next, behavior predictions of others. Autonomous vehicles must predict the behavior of other road users, including drivers, cyclists, and pedestrians. These predictions are inherently uncertain because human behavior is complex and variable. Probabilistic models such as Bayesian networks and inverse reinforcement learning allow the vehicle to estimate the likelihood of different actions based on observed behaviors. For example, the vehicle can predict whether a pedestrian is likely to cross the street or whether another driver might change lanes. By continuously updating predictions based on real time observation, the vehicle minimizes certainty and improves safely in dynamic traffic scenarios. Next, there is handling the so finally that next we'll go to the example problems. What is the basic probability? How we are using the probability? We'll see some basic probability concepts. Say for example, if you are taking the sample space, considering the symbol it as yes, the set of all possible outcome of what do you mean by sample spaces? It is defined as the set of all possible outcomes of an experiment. Say, for example, when rolling a six-sided die, the sample spaces, what are all the options will be there? 1, 2, 3, 4, 5, 6. There is one die we are taking. In that, if you are throwing or rolling, we will be getting six options. Name that is called 1, 2, 3, 4, 5, 6. And the event E is defined as a specific outcome or group of outcomes from the sample space. Example, if you are taking the example, the event rolling an even number in the same case from the die. Even number 1, 2, 3, 4, 5, 6. What are all the even numbers? The even numbers are 2, 4, and 6 are the even number. So, event is represented by the symbol capital E is equal to 2, 4, 6. What is the probability of the event? We have to find out the probability of the event. The likelihood of event E occurring is calculated as probability of E. This even E represents what? Event. Probability of the event. Here, what is the problem we have taken? If you are rolling the die, rolling an even number, 2, 4, 6. So the number of favorable outcomes divided by total number of all possible outcomes. Here, how many total number of possible outcomes are there? 6. If you are throwing a die or rolling a die, you will get three numbers or there, that is 3. Or the rolling an even number. So the probability of the event is given by number of favorable outcome divided by total number of all possible. So for a die, the probability of rolling an even number is 3 divided by 6. So what is P of even? Is equal to 3 by 6 is equal to 5. If you want to calculate it in percentage, 0.5 into 100, so 50 percentage. Even number 50 percentage. What is the remaining from this? If you are asking what is, if you are rolling the die or rolling an odd number is also the same, 3 by 6 odd number, also 6.5. You get a 50 percentage. Next, what are all the key probability rules? So additional rule. If A and B are two events, the probability that either A or B happens, that is additional rule is given by probability of A union. This is the union equal to probability of A plus probability of B minus probability of A intersection B. So one more time I'll tell you, the additional rule is given by if you are using two events, if A and B are two events, the probability that either A or B happens is given by probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Example, the probability of drawing red or a face card from the deck of cards that we'll discuss in this slide, end of the slide. Multiplication rule. If A and B are independent event, here two event, the probability that A and B happens is given by probability of A intersection B is equal to probability of A into probability of B. Answer is probability of A and probability of B. Say for example, the probability of flipping a coin and getting heads, then rolling a die and getting 3. So the probability of head and two events we are taking. Tossing a coin, in that we wanted to get only head, and if you are rolling a die and we wanted to get a 3 in the die, 3 dice. Okay, in the coin we wanted to get head. So two events we are using. So here how you have to write is probability of head and the probability of flipping coin and getting heads and then rolling a die. So probability of head and 3 is equal to probability of head into probability of 3. So the coin, if you are tossing, there are two options. 1 by 2 is for head and 1 by 2 is for tail. Probability of head is equal to 1 by 2. Probability of 3 is equal to 3 by, that is 3. 3, oh, how many numbers are there? 3 is equal, only 1, 3 is there. In this case, 3, only 1. So 1 by 6. So here and probability multiplication rule, 1 by 2 into 1 by 6 is equal to 1 by 2. This is the best example. The chord, there are 52 chords in a standard deck of chords we are considering. In this deck of chords, this is the sample of chords or the chord colors. In this, there are 52 chords in the standard deck chord. There are 4 suits. What are all the 4 suits? Diamond, clubs, hearts, and spades. Diamond is given by this symbol. Clubs are given like flower, it will be there, and heart in means hearts, and this is the spade. There are 4 suits, or are they? Diamond, club, hearts, and spades. Face cards include, this will include in all 4 cases. This will be including. This will be having Jack, Queen, and King. And black cards includes all clubs and these clubs and spades are having the black cards, and the diamond and hearts or the red cards. Red cards include the all hearts and diamonds. Hope understand this picture, everyone. And the basic structure, how we can define, as I said, the standard structure consists of 52 cards. Each is we have 13. So 4 into 13, 52 cards. Four suits. What are they? Hearts, diamonds, clubs, and spades. Each suit has 13 cards. Ash to king. This first, we are not calling it as one ash. Ash. We can call it as ash. Then we can start it as 1, 2, 3 up to 9, 10. Then jack, queen, and king. 20 to 26 cards are red cards and 26 black cards. 12 face cards. What are they? Jack, queen, king. So 4 into 3, 12 face cards. And the types of events include sample events, drawing a king or queen. Drawing a king. In which case we are drawing a king, they have not specified. Generally, they are saying king or queen. So four kings are there, four queens are there in the cards. So compound event, we can write it as drawing a red card followed by the face card. We can say like this. And in this case, we'll see dependent and independent events. Also, we have a mutually exclusive event. How we can call it as drawing a king or an ash. This we can call it as a mutually exclusive events. And the key formulas, as I've said, number of favorable outcomes divided by total outcomes. So, OR operation, if you are using, we can write it as probability of A plus probability of B minus probability of A intersection B. We can call it as intersection. And the probability of A and B, we are calling it as independent events. In this, we have seen here, no? Independent events, we are using multiplication rules. If you are independent event, that is the dependent events. Independent events, if you are using, we are writing it as probability of A and B is equal to probability of A into probability of only multiplication. This term will come. So probability of A given B, we are calling it as probability of A given B is equal to probability of A intersection B divided by probability of B if it is dependent. Independent means probability of A into probability of B. Dependent means probability of A intersection B, A intersection B, whatever it is coming down, we have to write it as. Suppose probability of B given A. How will you write? Probability of B intersection A divided by probability of A. So in the deck of cards, in this figure, the deck of from this, we are solving some problems. So the king, how many kings are there? Four cases, four kings are there. So the probability of king is given by 4 divided by total number of cards, 1 by 13. Probability of drawing a red card. So how many red cards are there? Here 13. How many red cards are there? Yeah, 13, totally 13. So total red cards are 26 red cards. So how will you calculate the probability of red cards? The probability of drawing a red card is equal to 26 divided by 52 is equal to 1 by 2. So probability of face cards, what are they called? Face cards. Here 3, here 3, here 3 and here 3. That is Jack, Queen and king or the face cards. So totally 4 into 3, 12 cards. So the total number of probability of drawing a face card is 12 divided by 52 is equal to 3 divided by 13. Probability of ash or a king is equal to 8 divided by 52 is equal to, we can write it as 2 divided by, so as or a king means ash 4 plus king 4. So we write it as 8 divided by 52, 2 divided by 30. Probability of 2 ashes in a row. 2 ashes in a row means 4 by 32 we have to write. 4 by 52 into here 2 ashes in a row. 2 ashes in a row, 4 by 52 into 3 by 51 is equal to 1 by 221. Hope you understood this slide. So this is the picture of two dice. This is one die. This is two. In the previous example, we have seen one die is if you are rolling, what is the probability? Here, two dice at a time simultaneously we are throwing. We will get a 6 into 6, 6 into 6, 36 combination. We will get this outcome. So if you are throwing a two dice. This is the die 1, this is dice 2. So there may be 36 options. If both are throwing at the same time, we may be getting the option 1 1 or 1 2. In this case 1, in this case 2 maybe. Or otherwise this is 1 and this is 3, like that, 1 4 1 5 1 6, or 2 1 2 2 2 3, and up to both the ties. If you are throwing, sometimes you may be getting 6 6. So the totally 6 into 6, we have 36 outcomes we are getting if you are throwing this two dice, paired dice. In this we will solve some problems. So each die has 6 faces numbered 1 to 6. Rolling two dice means there are 6 into 6, 36 possible outcomes. Outcomes are represented as ordered pairs. Die 1, this is die 1, and this is die 2. So we are writing total number of outcomes are 6 into 6 is equal to 36. So how will you write 1 comma 1, 1 comma 2, 1 comma 3, etc. Up to 6 6. So totally 36 outcomes will be there. We are getting 36 outcome. Each outcome is equally likely with a probability of 1 by 36. So possible sums, if you want to 2 to 12, this is the example, sum of two dice. Different outcomes for each sum. Sum if you are getting 1 comma 1, if you are adding 2 we are getting. Sum 3 means there may be two options, 1 plus 2 or 2 plus 1. If you are looking into the table, you can able to find out. From this table we can calculate n number of problems. 36 combinations may be 1 comma 3, 2 comma 2, 4, 3 comma 1. So what is the probability that we have to see? Combinations 3 divided by sum of 12, only one combination, 6 comma 6, 6 plus 6 is 12. So what is the probability of sum? Probability of sum is given by number of favorable outcomes divided by 36. So sum of 7 means how many combinations? 6 combination divided by 36, 1 by. Sum of 2, so in this case, sum of 2, how many combinations will be there? 1 comma 1. So only 1 divided by 36. And sum 7 has the highest probability because there are 6 favorable outcomes. 1 6 2 5 3 4 4 3 5 2 6 1. So what is the probability for this 6 divided by 36 is equal to 1 by 6. So in this case, in terms of percentage, if you wanted to calculate, you will get a 16.67. So sum of 2 and 12 have only one favorable, that is 1 comma 1 and 6 comma 6. So how will you write 1 by 36 and 1 by 36? And bar graph, in this. So what is the, in this case, what is the probability of rolling the sum of 8? What is the probability? These are all the example problem. Probability of 9, probability of 5. What is the probability of rolling an even number? See here, sum of 8. Outcomes 2, 6, 3, 5, 4, 4, 5, 3, 6, 8. How many numbers? 1, 2, 3, 4, 5. So we'll write it as probability of sum is equal to 5 by 36. Doubles. Doubles means 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6. So totally 6 divided by 36 equal to 1 by 6. Sum is greater than 9. Outcome is 4, 6, 5, 5, 6, 4, 5, 4, 6, 5, 6, 6. So probability of sum is greater than 9 is 6 divided by 36. The outcome is 1 by 6. Less than 5, 1, 2, 1, 2, that is 1, 1, 1, 2, 2, 1. We have to calculate it from the table. This value is also 1 by 6. So even sum, 18 outcomes, the probability is 18 divided by even sum. How many even sums will be there? 18 outcomes. Probability is 18 divided by 36. So in this way, we can solve n number of problems. So hope everyone understood about the basics of the probability theory. We will solve more problems in the future. Next, we'll coming into the there is what is that? Applications of the probability. and it is used in the AML, making predictions and handling uncertainty mainly, and the finance, assessing investment risks and modeling stock prices. And healthcare is also, it has been used estimating disease likelihood and predicting treatment outcomes. And it probability empowers informed decision making across the multiple fields. So next, how this probability is used in AML example. First, the handling the uncertainty. How it has been used in handling the uncertainty. Probabilistic model play an important role in managing uncertainty in AML systems by predicting outcomes based on available data. For instance, in a spam deduction, probability is used to analyze the frequency of certain words in an email to determine whether it is a spam or legitimate. This approach allows AI models to make informed predictions in uncertain scenarios, ensuring that decisions are based on the likelihood of different outcomes. Next, Bayesian interface inference, Bayesian inference. This Bayesian inference enables AI models to update their beliefs dynamically as new data becomes available. This is particularly useful in environments where information constantly changes, such as self-driving cars that use Bayesian networks to assess the probability of obstacles and pedestrians appearing. By incorporating new data into existing models, Bayesian inference ensures that AI systems remain adaptable and accurate in real-time decision making. Next, model evaluation. Model evaluation techniques such as cross validation and performance metrics heavily rely on probability to assess the accuracy of machine learning models. In cross validation, the data is split into training and testing sets multiple times, and the probability helps evaluate how well the model is. So, how the model no, generates unseen. This process ensures the model consistently and minimizes the risk of overfitting and underfitting. Next, decision making. It is also used in the decision making. AI models use probability to optimize strategies and minimize the risk in complex environment. Say, for example, in a recommendation system, probability helps suggest movies or products based on users' previous preferences. Next, algorithmic efficiency. Many AI algorithms, such as naive-based hidden macro models, are rooted in probability, enabling them to perform tasks efficiently. The Naive-Bayes classifier based on Bayes' theorem is widely used for text classification tasks such as sentiment analysis and spam filtering. These algorithms rely on probabilistic principles to quickly analyze large data set and deliver accurate predictions. Also, used in the reinforcement learning. So in as a the in a game playing AI probability helps the agent choose no, especially is used in the chess like games, how it will take the decisions, AlphaGo decision making. Next, improved generalization. Understanding probability enhances model generalization and reduces the risk of overfitting by incorporating probabilistic regularization techniques. Say for example, dropout is a regularization technique used in neural network that randomly disables some neurons during training, preventing overfitting and improving model robustness. By improving generalization, probability ensures that AI models perform well on both training and unseen data. So these are all about how this probability techniques are used in the that is uncertain to solve the uncertain problems. So coming into the conclusion, understanding the foundations of probability theory now provides a structured approach to analyze uncertainty and predict outcomes in complex situations. By understanding core concepts like sample spaces, events, probability measures, we can make informed decisions. Its applications in AI, machine learning, and data science enhances decision making and model accuracy. Mastering probability theory equips us to handle uncertainty effectively in various domains. So, thank you for exploring the foundations of probability theory with me. The remaining things we'll discuss in the next lecture. Thank you.